All right, welcome back again, everybody. Today we're going to be doing section 5.4. This section is all about the binomial theorem and Pascal's triangle and a whole bunch of good stuff. Let me get the slides up and we'll get started right away. All right. Here we go. So this is actually the last section of chapter 5, building off of the stuff we learned earlier. We're going to start with just some motivation and exploring a couple patterns, you could say. Then we're going to talk about Pascal's triangle, which is a really, really nice, concise way of containing these patterns that we observe. Then we're going to talk about what the binomial coefficients are. We'll talk about the binomial theorem. We will do a bunch of examples using it, and then we'll get some helpful Mathematica commands at the very, very end. All right. So let's start with some motivation. I always like to start with some motivation. You might remember that earlier in the course, I said something along these lines that exponents don't play well with sums and differences. So today we're going to answer the question, what does that mean? What do I mean when I say exponents don't play well with sums and differences? And if that's the case, how do they actually play together? How do they play together? And we're going to figure that out today, okay? So the way we're going to do that is we're going to start by looking at some patterns. First, I want you to consider the binomial a plus b. Binomial just meaning it has two terms. That's basically it. So we have a binomial here, a plus b. And what I want to do is I want to expand some integer powers of this binomial and look for patterns. So I've got a few listed out here, starting from 0 and going up to 5 and then beyond. So a plus b to the 0, well, that's 1, right? Anything to the 0 is 1. A plus b to the 1 is just a plus b, nothing special going on there. A plus b squared, this one you should know. This is one of those special factor forms to memorize because it's a perfect square trinomial. It factors, or I'm sorry, it expands into this form. And what does a plus b cubed look like? Well, if you go and multiply all this out validly, you will get this. And remember, exponents don't play well with sums and differences, so you can't just distribute the 3 to a and the 3 to b and call it a cubed plus b cubed. That's not going to be right. In fact, it's way, way, way off from the correct answer. So the difficulty with these types of expressions is if you want to compute a plus b cubed, you guessed it, you're going to have to do a plus b times a plus b times a plus b. And if you want a good exercise, you can try this right now. Multiply this out, factor by factor. So do a plus b times a plus b, and then the result that you get there will actually be this. And then take a and multiply it by every one of those terms, and then do b and multiply it by every one of those terms, add the results, simplify the results, and you will get this. All right. So this is why I say exponents don't play well with sums and differences, because there's a lot of cross-mixing going on when you do the multiplication process. So a plus b cubed looks like this. A plus b to the fourth is going to look like this, right? A plus b to the fifth, if you go through and you multiply them all out by hand, you will get this. And then on and on and on, okay? So the question is, what if I had any integer power of a plus b? What is a general structure for that power of that binomial? And what I want you to do for a minute here is just stare at this list of expressions or equations and see if you notice any patterns. So you can pause the video, just take some time, look for any patterns that you see. All right. Now try to verbalize something. If you're watching this with your peer or your friend, talk to each other and talk about what you're noticing here. If not, then you can just talk to yourself. That's okay. Don't feel bad. Just give your brain that feedback so that things will click a little better. What do you see? Okay. All right. Now, let's take note of some patterns together for a minute here. So first thing, for each n, meaning for each one of those exponents, there's n plus 1 terms in the expansion. So notice here, when it was 0, there was 1 term. When it was 1, there are 2 terms. When it was 2, there are 3 terms. When it's 3, there's 4 terms. When it's 4, there's 5 terms. Is that right? One, 2, 3, 4, 5. And in general, whatever this n is, there's going to be n plus 1 terms. That's one pattern to notice. Another one, notice that each expansion began with a to the n and ended with b to the n. Let's look back and see. Look, a to the 1, a squared, a cubed, a to the 4th, a to the 5th, right? It's matching that power there. And then ending with b squared, b cubed, b to the 4th, b to the 5th, just like that. So that's another pattern to notice. Other patterns, the powers of a counted down from n to 0, remembering that a to the 0 is 1. So let's look. Oop, come here. There we go. Yeah, okay, so check this out. Let's look at this one for a minute. It goes a cubed, and then you have a squared, and then you have a, and then you have a to the 0, which is 1. So same thing there. A to the 4th, a cubed, a squared, a to the 1, a to the 0. A to the 5th, a to the 4th, a cubed, a squared, a to the 1, a to the 0. So basically the powers of a are counting down from n to 0. Similarly, the powers of b are counting up from 0 to n, remembering that b to the 0 is 1. So here we go. Like we'll start here again. So b to the 0, b to the 1, b squared, b cubed, right? B to the 0, b to the 1, b to the 2, b to the 3, b to the 4. All right. B to the 0, b to the 1, b to the 2, b to the 3, b to the 4, b to the 5. So we got a lot of patterns here. There's a ton of structure, and we can generalize those structures using those patterns that we noticed, all right? So what is the pattern in the binomial coefficients? Let's start with that, actually. So here, all of these patterns we noticed, but are there any patterns in those coefficients? There's something that we haven't talked about yet. We talked about the powers of A, the powers of B, the number of terms in each expansion. But what about these coefficients? 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. Is there a pattern there? That's the question. That's this final question, right? And if we can find a pattern there, then we have basically found a whole bunch of patterns that mush together to give us the structure of those binomial expansions. So it turns out that these things do, the binomial coefficients do follow a nice pattern, and they're very well collected in this thing right here. So if we list out those coefficients in a triangular array, we get the following. When n is 0, it was just 1. When n was 1, we got 1 and 1. Let me flash back, right? When n is 1, you got, oh, sorry, 1 and 1. When n is 2, you had 1, 2, 1, and so on, right? So this is just listing out the coefficients in each one of those expansions, like that, like that, like that. And just writing them out in this array is going to reveal a very, very cute result, a cute pattern, okay? This thing here is what's called Pascal's triangle, all right? So that triangle is called Pascal's triangle, and what it does is it provides the binomial coefficients of a binomial expansion. And it uses a very basic formula that I've kind of illustrated here in this figure. If you want to get the coefficient in the next row, you add the corresponding coefficients in the previous row. So how do we get this row here, for example? Well, we take the row above it and we add the terms or add the coefficients pairwise. So there's always a 1 on the diagonal here and the diagonal here. We saw that in the expansions. How did I get 2? I added 1 plus 1 to get 2. Now for this row right here, I'm going to do 1 plus 2, which is 3, 2 plus 1, which is 3, and then 1's on the outside still. For this row right here, well, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and that's the pattern, right? We'll do one more just for edification here. 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and so on. So there is a pattern. There's also a symmetry there, right? That's why we're seeing that triangular array. That's it. So this is actually how you produce the next row of coefficients using that algorithm of adding the previous two, adding the previous terms to get the next one. And we will prove that at the end of this section. But these coefficients also play an important role in combinatorics and probability, which we will not really discuss, but we're going to get some notation for it at least. All right. So the binomial coefficients. The binomial coefficients, they're realized by what's called a combinatorial argument. You'll talk about that in a discrete math course or sometimes a statistics course. It has to do with combinations, permutations, probability, statistics, that kind of thing. But we're going to introduce a new notation to express what these binomial coefficients are. And it's this symbol. So the binomial coefficients are given by this symbol here, right? It's like two big parentheses with an N and a K. And this symbol is read N choose K. Now, if you took a stats course before or learned a bit about combinations and permutations, you might have heard this before. N choose K is just the number of ways to choose an unordered subset of K objects from a set of N objects. So maybe a more concrete example would be, if this said like 10 and this said 3, that would be how many ways can you choose groups of 3 from a set of 10 objects? Right? And this symbol represents that quantity. How many ways you can choose groups of 3 from 10. That's it. So we say n choose k, like 10 choose 3. And that's what this symbol represents. A lot of times you will see a symbol like this to represent that same one, standing for n choose k. It just kind of depends on the textbook or the context, but this is a very common one. All right. Now, how do we actually compute that? I mean, we saw Pascal's triangle giving us that formula, but is there an algebraic formula that doesn't rely on just using a geometric intuition of adding two things above and then getting a number below, right? Well, there is a formula for it, and it's this one right here. And again, this formula follows from a combinatorial argument, which we won't get into, but you'll learn later on. So let n and k be non-negative integers where n is greater than or equal to k, then the value n choose k is equal to this expression, n factorial over k factorial times n minus k factorial. All right, so this is the formula for the binomial coefficients using the factorial function. One note I will say, this is a formula that you do need to memorize. You do need to have this one in your back pocket because you're going to use it a lot. It's not as painful as it may seem. You're going to see in a minute once we do some examples, but you do want to know this formula. N factorial over k factorial times n minus k factorial. And we're going to do some examples using it in just a moment. Right, let's do a couple examples now. So let's practice this. Let me think. Okay, we'll do this. Okay, let me say this. I will do these first two first, and then I'll leave the second two for you to do on your own, just so I can show you some patterns that can help you simplify these things. All right. So let me do these first two together. So 5 choose 1. We're going to use that formula for the binomial coefficients with the factorial function involved. So yeah, we've got 5 factorial because here, again, n is equal to 5 and k is equal to 1. So we get 5 factorial over 1 factorial times 5 minus 1 factorial. 5 minus 1 is 4. Remember, 1 factorial is just equal to 1. So that's just going to be 1. That's not going to do anything. And we're just left with 5 factorial over 4 factorial. Now what I'm going to do is I'm actually going to expand 5 factorial and 4 factorial just so you can see this cancellation process occur discretely, I'll say. So 5 factorial is 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And we have a bunch of common factors that we can cancel. And then what we're left with is 5. So 5 choose 1 is 5. All right. 6 choose 3. Now in this case, n is equal to 6 and k is equal to 3. So just like before, we've got 6 factorial over 3 factorial. 6 minus 3 is equal to 3. So we've got that. Now what I'm going to do is I'm going to kind of partially expand 6 factorial using that recursion relationship for the factorial function that we talked about back in section 5.1, right? So I'm going to rewrite 6 factorial as 6 times 5 times 4 times 3 factorial, right? Because 3 factorial is 3 times 2 times 1. Then I can cancel one of these 3 factorials just like that. Now I'm going to expand the other 3 factorial as 3 times 2 times 1, and there's a bunch more cancellations that occur, right? So 6 is equal to 3 times 2 times 1, so I can cancel 6 and 3 times 2 times 1, and then what I'm left with is 5 times 4, which is just 20. So just to give you maybe some intuition for this, this is 6 choose 3. So if you had a group of 6, or if you had a set of 6 and you wanted to know how many ways you could choose 3 items from that group, there are 20 ways to do that. So maybe if you had a group of or maybe if you had like a class of 6 students and you wanted to know how many ways you could form groups of 3, there's 20 ways to do that, unordered groups of 3. All right, so I want you to try the other 2. So I want to leave these 2 for you to try, and then we'll do them together in a minute. So think about it for a moment. All right. And now say something out loud. Maybe what's that formula, right? So try to say that formula for n choose k out loud. And if you don't remember it, go look back at it and then say it out loud to yourself. All right. And now try to work them out and we'll do it together in a minute. Just a little bit of a heads up. You are probably going to need a calculator for that one because that's going to be a really big number, as we'll see. Okay. All right. Now let's do it together. Here we go. So same kind of process as before. In this case, n is equal to 9 and k, oops, and k is equal to 8. So here's the formula again. 9 minus 8 is 1. 1 factorial is 1. So here we're going to get 9 factorial over 8 factorial. And we're going to use that recursion relationship again because 9 factorial is 9 times 8 factorial. So we can cancel the 8 factorials and we've got 9 in the end. All right, now this one is actually a very large number. So n is 75 and k is 25. So how many different ways can you choose 25 objects from a collection of 75 objects? There's a lot. There's a lot. But going through the formula again, you can see this is what it looks like approximately, right? Or exactly, not approximately, exactly. 75 minus 25 is 50 factorial. And then you could try to go through and expand this. You could write 75 factorial as 75 times 74 times 73 times 72 times 71, all the way down to 51, and then do times 50 factorial, and then cancel this, or cancel the pieces there, right? But um, still going to be a lot, right? You're still going to have to do 75 times 74 times 73 times 72 times 71. You're going to have to multiply a lot of things together. And when you do, you get this gigantic number here. Geez, I'm not even sure how big this is. Let's see. What is this? Millions, billions, trillions, quadrillions, quintillions. So 52 quintillion, 588 quadrillion, uh, 547 trillion, 141 billion, 148 million, 893,628. Just gigantic numbers. Remember, the factorial function grows extraordinarily fast, face meltingly fast, and you're seeing it manifest in these problems as well. Okay, now there's a couple things you might have noticed with some of these questions. In particular, this one gave the answer 5, and this one gave the answer 9, right? So they both gave n in this case. So there's a couple of really handy shortcuts for some of these particular coefficients. So they're basically given right here. So n choose 0 is 1. The number of ways you can choose 0 objects from n is 1. N choose 1 is n. The number of ways you can choose 1 object from n is n. N choose n minus 1 is n. Oop, come back. There you go. N. And then n choose n is 1. So these are just handy properties to remember, handy calculations to remember for when you're working with n choose k. Okay, now we are ready to state and look at what is called the binomial theorem, the name of this section. So here is the binomial theorem. For any real numbers a and b, for any whole number n, we have this. A plus b to the n is written like this in expanded form, and then we're going to get this closed form in a minute, but I want to walk through it. N choose 0. Look at the coefficients first. N choose 0, n choose 1, n choose 2, n choose I, dot, 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 n choose n minus 2, n choose n minus 1, n choose n. So there's that pattern in the coefficients. And then look at the patterns of those other factors, a to the n, a to the n minus 1, a to the n minus 2, dot, dot, dot. B to the 0, b to the 1, b to the 2, dot, 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 all the way up to these results. So this is why we like sigma notation and summation notation, because nobody wants to have to write this out every single time. Instead, we can compact or compactify everything using sigma notation. It is the sum from k equals 0 to n of n choose k times a to the n minus k times b to the k. All right? Let's look at this real quick. Let's look at some of these. Let's look at some of the structure here. N choose k is giving you those coefficients that we saw in Pascal's triangle. Pascal's triangle gives you those coefficients. So as long as you know Pascal's triangle, you know those coefficients. The only downside with Pascal's triangle is you have to know the previous row to get the next one. So that can be kind of frustrating. Whereas the formula that we just got for n choose k using the factorial function, that's a closed formula, so you can just calculate it using that. A couple other things I want to point out. Notice the exponent of a. It's n minus k. So that's showing you how the powers of a are decreasing as k goes from 0 to n, right? Remember it was like a to the fourth, a cubed, a squared, a to the 1, right? And then there's b to the k. And here this k is indicating the powers of b are going up. It's b to the 0, b to the 1, b to the 2, b to the 3. So this is that structure for giving the ascending and descending powers of a and b. And that kind of puts everything together, right? We have the coefficients, we have the descending powers of A, we have the ascending powers of B, and we know we're going from 0 to n, and that gives us the expansion of that binomial. So that's what this is. The binomial theorem gives us an explicit and really a concise formula for the expansion of binomial powers. Now, in calculus 2, you're actually going to generalize this result so that the exponent here, n, can actually be any real number. It doesn't just have to be a whole number, right? Which is pretty wild. This is one of the reasons why, we when we're stuck with whole numbers, we can build some good intuition, but it turns out that we can generalize that to be just real numbers. But the mathematics to do so is pretty subtle, and you're going to need some calculus to do that. Moreover, it turns out that this theorem can be generalized for powers of polynomials. This is just a binomial, two terms, right? Bi means two. So this is just two terms. It turns out there is a formula if you have three terms and four terms and five terms and six terms and however many terms you want for any polynomial. That's it. So in general, that is what's called the multinomial theorem. So the binomial theorem, which we are studying, is actually a special case of the multinomial theorem, which is a more general version of this thing right here. Maybe as a little side note, because we now have the tools to understand a little bit better the formula that we saw way back in section 5.3 when we were talking about the Weierstrass approximation theorem. Let me pull up Chrome one more time, and I want to take a look at that that approximation we explored a couple chapters ago. Okay, here we go. So, do you remember we had this really gnarly formula back in section 3.5? And the whole point here was that this represents a polynomial or a sequence of polynomials that better approximates the absolute value function. And as n increases, we had this behavior, right? Okay, so take a deep breath for a minute. Remember, we control the math. It's not controlling us, okay? this, you actually have enough knowledge to understand what's going on here. The only thing that's missing is that this is representing a function, and that's what you learn about in calculus 2. So here, these are the coefficients. Those are the binomial coefficients. N choose R. N in this case is 1/2, and K is K. And then these are what the other factors are going to be for each one of those terms in that binomial expansion. All right. Now, stuff that you'll study in calculus 2, here we have another variable x. And so this finite summation actually represents a function. And in fact, it represents a polynomial, where this is giving you the coefficients of the polynomial. And this is kind of giving you the other part of those terms. All right. So this is what you're building up to when you get to Calc 2. So what have we talked about in this course? We've talked about summation notation. Come here, highlight it. There you go. We've talked about n choose k or n choose r. We've talked at length about what functions are. We've talked about what polynomials are. And when you get into the calculus sequence, you get to put all of that stuff together in just these really magical, beautiful ways. Okay? I'm excited for you. Okay, tangent over. Let's go back to the slides. Um, where was I? What was I talking about? Oh, yes, that's right. That's right. Okay, so now baked into this theorem, we have a really nice corollary. It's this one right here. This formula basically yields this. The k plus 1th term in the expansion of a plus b to the n is given by this formula. So let's say you've got an expanded binomial and you want to know what the eighth term is. You know, maybe in this case n is 50, but you want to know what the eighth term is. Well, you can compute that because the terms follow this pattern. So the k plus 1th term is going to be whatever this expression evaluates to when you plug in your numbers for n, k, a, and b. All right. One little subtle detail there, it's the k plus 1th, and that's because k starts at 0 in that binomial theorem expansion. All right. Okay, now let's do some examples, right? Let's practice for a minute. I want you to try this one on your own because this one is relatively simple. But I want you to expand x plus 3 to the 5th. I don't want you to do it by hand. I want you to try to use the binomial theorem and Pascal's triangle, okay? So think about it for a sec. All right. Now verbalize something. Maybe try to say uh, maybe what you remember about Pascal's triangle or what you remember about the binomial theorem. Right. And now try to work it out on your own. Remember, Pascal's triangle gives you the coefficients of the terms, and remember the descending and ascending powers. Okay, here we go. In fact, yeah, here we go. Okay. So here I expressed it using the binomial theorem, but it'll be fine. So remember, the coefficients are going to be 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. And then we're going to have ascending powers of x and descending powers. I'm sorry, I have that backward. Descending powers of x and ascending powers of 3. So x to the 5th, 3 to the 0, x to the 4th, 3 to the 1, x cubed, 3 squared, x squared, 3 cubed, x to the 1, 3 to the 4th, x to the 0, 3 to the 5th. And now we just evaluate, we simplify, we compute, and that's about it. Okay. So 3 to the 0 is 1, 5 choose 0 is 1. So this is going to simplify to x to the 5th. This term here will be that 5 times 3 x to the 4th. This term here will be this 10 times 9x cubed. This one is this. This one is this. And this one is that. And then you just continue to simplify. Um, excuse me, the numbers might get kind of large, but they will be accurate. They will be exactly what those numbers are. And there it is. Right. Okay. Now here's another example. Let me see. Do I want you to try this one? Hmm. Okay. I'll tell you what, I will do this one. If you want to try it on your own, you can, but I want you to try the next example after this one. Okay, so here we're going to expand this binomial power because I want to show you a little bit about how to do it because this one is actually a subtraction. That's okay. It doesn't matter if it's subtraction or addition. The only thing here is we're going to rewrite this as the sum of a negative number. Okay, so that's like the first step. So we can rewrite 3y minus 2 to the fourth as 3y plus negative 2 to the fourth. And then we can use Pascal's triangle and we'll get the coefficients and then we just got to go through the rest of the calculations. So here we go. Pascal's triangle gives us the coefficients 1, 4, 6, 4, 1. We've got 3y to the fourth, 3y cubed, 3y squared, 3y to the first, 3y to the 0, right? So the descending powers of the first term. And then here, this is negative 2. So we're going to have negative 2 to the 0, negative 2 to the 1, negative 2 to the 2, negative 2 to the 3, negative 2 to the fourth. And that's the structure. So once you've got this written out, the rest is just massaging all the kinks out of it, right? So simplify this term, oops, too much, this term, and this term, and you get this. Remember, it's okay to do intermediate steps. We've got powers of a negative number here, so you got to be careful with the negative signs. For me, I would just write this intermediate step so that I don't get lost, because I would easily get lost. Negatives and negatives times negatives, that throws me off a lot personally. All right, so what I'm saying is I'm just going to keep it as like that, 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 and then do another simplification step in which I get this. So 3y minus 2 to the fourth is equal to this. How cool is that, right? How cool. You don't need to do it by hand. You don't need to do 3y minus 2 times 3y minus 2 times 3y minus 2 times 3y minus 2. You can use the patterns that we've explored in this section. All right, now here's one that I want you to try, okay? So I want you to find the seventh term in the expansion of this binomial, 3x plus 2y to the 10th, all right? So ponder that for a second. Okay. Now say something out loud. Maybe do you remember the formula for the k plus one-th term in a binomial expansion? All right. Now try to work it out on your own. My little hint or my little tip is remember that the formula we got was for the k plus one-th term. So 7 is the k plus one-th. K. 7 is k plus 1. So what does that make k equal to? All right. Now let's do it together. Okay, so since we want the seventh term, k plus 1 equals 7, and so that means k is going to be 6, right? K is going to be 6 because k plus 1 is 7. Here, n is equal to 10, a is equal to 3x, b is equal to 2y, and so that corollary tells us that the seventh term is going to have this structure right here. Now we just go through all the cleaning, right? Got to massage all the kinks out, organize everything, cancel things, simplify. So here we go. 10 factorial over 6 factorial. Well, I can expand 10 factorial a little bit. There's a 6 factorial baked into it, which I can cancel, and I'll just be left with 10 times 9 times 8 times 7. 10 minus 6 is 4, so that leaves me with a 4 factorial. And then 3x to the fourth is 81x to the fourth, 2y to the sixth is 64y to the sixth. And then at this point, you could simplify even more, right? For example, 4 factorial is 4 times 3 times 2 times 1. So it's got a 4 times 2 in there, but 8 is equal to 4 times 2. So we can get rid of that. And then we're left with a 3. But 9 has a factor of 3 in it, so we can cancel that 3. So baked into these two factors is 4 factorial, and you can simplify them in that way. That's why we've got a 3, and then the 8 is totally gone. So we're left with 10 times 3 times 7 times 81 times 64, and then the variable factors here. And then this is where I would go to a calculator just to save some time because that's going to be this 1,088,000 8,640. So if you were to expand this out, this is telling us that the seventh term in that expansion would be this, would be that. Pretty cool, huh? A nice little shortcut. All right. Now, to kind of wrap things up, I do want to prove a technical lemma. So we stated this earlier in the lesson that we had a formula, or that Pascal's formula produced those binomial coefficients, and we're going to prove that now, just so that we can use Pascal's triangle with confidence. Okay, so here is the technical lemma that we're going to prove, and the reason I want to do the proof also is because it has a lot of techniques that we have seen before, but shown in something that might look more complicated. All right, we're going to make sense of it together here. So the algorithm to produce the entries of Pascal's triangle produces the binomial coefficients. This is what we're going to prove. In other words, more technically speaking, the kth entry in the n plus 1th row of Pascal's triangle is the sum of the k minus 1th and kth entries in the nth row. This is that whole idea of this. Let me flash back for a minute. It's this. It's this idea. We're going to prove that this is true. That if you want to that if you want to get these, that's what you do. You add those two things because these rows are given by the binomial coefficients, and we're going to show that Pascal's triangle and doing this process is actually valid. So here we go. All right, where was it? Go back, go back. Right here, this is the technical statement that we're going to prove. N plus 1 choose k is equal to n choose k minus 1 plus n choose k. This is like the, you know, taking this plus this gives you that, like so. All right? Okay, so we're just going to use the definition of n choose k and the recurrence relationship of the factorial function, and we're going to multiply by a couple of clever ones to get this. Whoa, okay, okay. It's okay. Don't worry. It looks very complicated. We're just going to follow our nose. We're going to look at the pieces, and you will be able to make sense of every single thing that you see on this page in about 1 minute, okay? So here we go. Hang on, take a breath. N choose k minus 1. Just using the formula, we get this, right? Here's the k factorial. Here's the n minus k factorial, except this, in this case, the k is k minus 1, right? So that's this right here. And then n choose k is just simply that. All right, now we're going to multiply by some clever ones, but really all we're going to do is we want to take this sum of fractions and write it as a single fraction by finding common denominators. That's all we're doing here. So this step looks, gross, looks very complicated. We're just finding a common denominator. We've done that before. You know how to do that too. Just look at what this denominator is missing and what this denominator is missing, and then multiply by the appropriate one. In this case, it's k, right? And in this case, it's n minus k plus 1. Why is that the case? Well, remember, k times k minus 1 factorial is k factorial. Let me write that out. K times k minus 1, oops, factorial is equal to k factorial. That's the recursion relationship of the factorial function manifesting here. Okay, now this is how this is becoming this. And then here, this one's missing the n minus k plus 1 right here. So then when we do that, we're going to get this. There it is. And and again, this right here, this product is going to be n minus k plus 1 factorial because, again, the recursion relationship for the factorial function. That's how we're getting that. Now we have a common denominator. And since we have a common denominator, we can write this as a single fraction where we're adding the numerators. Okay, now we're going to do another thing that we've seen a bunch of times already, which is we're going to factor out common factors. Ooh, wait, hold on one second. Hang on. Let me be sure. Yep. Okay. Yep. That's right. All right. So we're going to factor out common factors. Here we go. So what do I see common between this term and this term? An n factorial. I see a common factor of n factorial here and here. So we're going to factor it out. And then we're left with this. Well, the k's cancel, and we're just left with n plus 1. But hey, once again, n factorial times n plus 1 is n plus 1 factorial. Down here, n minus k plus 1, I'm going to write it as n plus 1 minus k. And then if you look very carefully at this expression, it is in the form of n plus 1 choose k. N plus 1 factorial over k factorial times n plus 1 minus k factorial, which is n plus 1 choose k. There it is. So we've proven it. Here's our chain of equalities. We just proved that this is equal to this. So Pascal's triangle is indeed giving you the binomial coefficients in a binomial expansion. Okay. All right, real quick at the very end, just to finalize some things, there are a couple helpful Mathematica commands if you want to dig into them. I'm not going to show any examples because it's really just plugging in this formula. The Mathematica command binomial, n comma k is equivalent to n choose k, and it will give the corresponding binomial coefficient. So if your n and your k are rather large, Mathematica can help. As we've seen before, the Mathematica command expand is a really, really robust command. And if you need to expand a binomial, it can do it instantly. If you want to compute, 100 x to the fourth plus y to the eighth, all of that raised to the power of 1000, it can do that for you just by using the expand command. All right. Okay, on that note, let's play. All right, I hope you enjoyed this. This is the end of chapter 5. We've covered all the stuff we needed to cover there. The next chapter is the trigonometry chapter, and that is a great one. Trigonometry is fundamental, it's powerful. There's so much math and science that is based on trigonometry, so I am super excited to talk to you all about that one. Okay, so I'll stop rambling. Thank you all again for watching, and I will see you in chapter 6. Have a good one, everybody.